Assalamu alaikum. Hello, everyone. Today we will start a new topic, the topic of basic classification methods. For the first part, I have prepared a couple of slides that can actually explain this in a more visual way, and then we will come back to this file. Let me move to the slides here. So this slide actually explains like the difference between machine learning and data science, where they intersect and what are the differences between them, okay? Machine learning is actually, think of it like a set of mechanisms and techniques that can be used to enable artificial intelligence, okay? Some of these mechanisms or techniques, they learn from data, okay? Like, for example, supervised learning and unsupervised learning, as we will come to that later. In fact, regression is a one way where you actually build a model, you learn from data. So in order to learn from data, then we will run into this intersection between machine learning and data science, okay? Because learning from data is something that involves tools from both of them, okay? There are, like, for example, machine learning mechanisms and techniques that do not rely on data. For example, reinforcement learning. In reinforcement learning, you actually learn from experience, okay? And we're going to come to what reinforcement learning is later on. So that's why they intersect in some part, but not every machine learning mechanisms require data in order to enable artificial intelligence, but many of them, they rely on data, and that's the reason of the intersection between machine learning and data science. Think of machine learning as applications for data science that are actually applications that are concerned about enabling artificial intelligence. And also data science have some other, of course, functionalities that it's not only some field that machine learning is using to enable artificial intelligence, but also there are some other functionalities for and topics for data science that has nothing to do with machine learning, okay? So now these are the three types of learning, okay? So we have supervised learning, unsupervised learning, and reinforcement learning, okay? Supervised learning, as the name suggests, okay, for the training data, you actually have labeled data, okay? So, like, for example, if you are training your model to perform classification, then for the training data, you have, for every sample in the training data, you have the actual label, the class label, okay? So from that, you train a model. Later on, you use it to predict labels for samples that are missing labels, okay? So both classification as well as regression fall under the category of supervised learning. In the unsupervised learning, the objective here is not actually to classify or predict a target variable, okay? So there's no target variable here. The objective is more of actually revealing the underlying structure and define how the underlying clusters, okay? So cluster the nodes. So later on in the implementation phase, if you receive a new point, you will be able to associate it to one of the predefined clusters, okay? These two, they learn from data, okay? Reinforcement learning is more of like learning by experience, okay? So what do I mean by that? So actually here, what all you need is input state, set of actions, and observed reward, okay? Let me explain it by an example. For example, if you want to train a robot to navigate in a specific area without from point A to point B without hitting any obstacles in between, okay? Then at any given time, the robot will be exposed to an input state. It could be a 360-degree view of the scene. It could be the current coordinates, whatever the state is. It's something we need to design for reinforcement learning. Then given that state, the robot will perform an action. Simple actions, like maybe like a set of 4 actions. You move forward, you move backward, you move to the right or to the left with a predefined step size. These are the 4 actions, for example, okay? Then based on the action that is taken, based on the input state and action that is taken, the robot will observe some kind of reward, okay? And the reward will be high if the agent doesn't, for example, hit an obstacle, or if it moves closer to the destination, the observed reward will be high. Otherwise, the observed reward will be very low. So by observing this reward for different actions, eventually the robot will learn, given like a state, what's the best action to take. Okay, eventually it will learn to navigate from the point A to point B without hitting any of the obstacles in the fastest way. So this is like a reinforcement learning at very high level. In this course, we're not covering reinforcement learning. Our focus here is in techniques, as I said, that use data to learn. So the supervised learning and unsupervised learning. And today's topic actually is all about supervised learning. In particular, we are interested in the problem of classification, okay? So, and there are two ways or two kinds of problems for classification. There is binary classification and there is multi-class classification. As the name indicates, binary classification is when we have two classes, and multi-class classification is when we have more than two classes. And we're gonna come to examples about both of them later on, inshallah. Okay, so one well-known method, okay, to perform classification is decision trees, okay? So let me start by defining decision trees, okay? Or what is a decision tree? A decision tree or decision trees in general are flowchart-like graph of all possible solutions to a decision. So if you look here into this figure, so actually a decision tree model is a model where you feed like an input sample with so you have an input sample with the number of features and values for different features. So you will feed it to this tree. So every node here is checking some condition in one of the features, okay? And then by checking that condition, so you will follow a certain path. Eventually you will reach a node, a leaf node that tells you this like this sample belongs to which class. And we're gonna come to more details later on, but here now at this level we want to be at very high level. We're gonna come to examples and explain how we build these trees actually later on, okay? Because maybe at the first time you think like, okay, if it's like conditions, then why it's considered as a machine learning algorithm. In fact, like how to build those conditions and what feature to choose at every node is actually something we need to learn, so that the size of the tree can be actually made very small, okay? If we like arbitrarily or randomly select things, then we may end up having very complicated tree and we run into many problems. And we're gonna come to explain those later on. Okay, so why it's called a decision tree? It's called a decision tree because it starts from a root node, as we can see here, and then branches off to a number of decisions, like a tree, right? So this is the root node, and the ones in the middle are inner nodes, and the ones like the last ones are the leaf nodes. Okay, it's a tree structure. It's just a flipped tree. Okay, if you flip it, then it's exactly a tree. Okay. And the goal, as I said, is to create a classification. In fact, it's also even used to create regression models, but our focus here will be on how to create decision trees for classification. I may later on, after we explain it very well for the task of classification, we may spend some time talking about decision trees for regression tasks. But for now, we are actually considering decision trees as classifiers, okay? So to predict the class label or the target variable based on a set of input variables, okay? The methodology is to break down a data set into smaller and smaller subsets, while at the same time an associated decision tree is incrementally developed, okay? Because in fact, think about it, during the training, you feed all of the input samples to the root node, okay? But some of them will satisfy the condition, some of the samples. So some of them, they will satisfy the condition. So we will move to the left, some will not, we will move to the right. And definitely as we proceed, the number of samples that is inputting to every node will be less and less. Eventually, here only, like hopefully only nodes belong to the same class will reach here or here, or and so on. Okay, And there is only one path you can go for every sample, okay? So if a sample satisfies the condition here, it's gonna come here. If it doesn't satisfy the condition we put here, then it will come to this one, or if it satisfies, it comes to that one. So there is always one path for every sample, okay? That's like at very high level, as I said, as of now, but we will come to more details later on. But let me first explain like why really we need to think about which feature and what condition to build at every node, why that's important. Let's consider this very simple example here I created. So here we assume like we have a number of input features, okay? We focus only now for the sake of the explanation, we focus on the first two features, okay? Simply these two features are teaching experience and research experience. So it's a 1 or 0. Okay, for simplicity now, okay? So we assume like a candidate, okay, who applies for a position at a certain university, okay, he will have 1 for this feature if the candidate has a teaching experience. Otherwise, he will have 0. He will have 0 for that. Same for the research experience. So 1 if the candidate has research experience and 0 otherwise. Okay, I know in physical world, like the research and teaching experience can be measured in years, but here just for the simplicity, okay? And here is the target variable, the label, okay? The class label. So 1, that means this person was given an offer. 1, the candidate who has teaching experience as well as research experience, he was given an offer. This one doesn't have research experience, and he has doesn't have teaching experience, and he has research experience, and he was also given an offer. This one has a teaching experience but no research experience, and he wasn't given an offer. Okay, so I think that's enough explanation for the data itself. Let's look at the problem here. Now we can design, how do we design like a decision tree here? Let's start like randomly, choose one feature at the root node. Okay, we choose this feature, the teaching experience, okay? So the teaching experience, and we build this condition, teaching experience greater than 0.5. We're gonna check that condition. Now, before we feed these samples here, so let's look at the uncertainty on this one, okay? So as you can see, we have in total 1, 2, 3, 4, 5, 6, 7, 8. We have 8 samples, okay? 4 of them have a value of 1, and 4 of them have value of 0. So they are equally probable. So if I randomly select one sample, it has equal probability to be 1 or 0. So the uncertainty is so high because those two classes, they are equally probable, okay? So then the uncertainty here is so high, okay? Now let me feed that here and check the condition. If I feed it to this, I will check the condition. 4 of them will satisfy that condition. 4 of them, like, will have, now I'm checking here, okay? The teaching experience. 4 of the samples have teaching experience that is greater than 1, okay? So they will come here. And 4 do not satisfy that condition. They have less, they don't have teaching experience. So the teaching experience is less than 0.5. But now, as you can see here, I have less uncertainty because from class 1, I have only 1 sample here. From class 0, I have 3 samples. There are more samples from class 0 than class 1. So there is less uncertainty. There is higher probability. If I pick 1 sample here, there is much higher probability that it belongs to class 0 than class 1. So the uncertainty has reduced. The same applies here, okay? Now let's add another level and let's put this condition, okay? Research experience greater than 0.5. Let's check this condition. So if we check this condition here, we found like we end up having only 1 sample here and 3 samples here. And this sample here belongs to class 1, and all of these 3 samples are belong to class 0. So there is no uncertainty here. I'm sure like all the samples that are here, they are belong to class 0. All of the samples here, they are belong to class 1. So there is no uncertainty here. Okay, the same applies here. Okay, so then every outcome here, every output will tell me the class or of whatever sample I feed, okay? So there is no uncertainty. Now, I could have actually done it this way, right? If I just build the first condition based on the research experience, then I feed the 8 samples. I found like from just 1 node, I was able to
actually classify all these samples, and I can have uncertainty here. So for the four who were given, who were belong to class 1, who were given an offer, they have research experience greater than 0.5. So they have research experience. And the ones they were not given offers, they actually do not have any research experience. So these two trees can actually do the job, can classify every input sample. Okay, they can classify it correctly. Okay, but actually this is much smaller tree compared to this one. Okay, so then the way, like what feature to choose and what condition to build can actually play a crucial role in making the tree size very small, because actually, as we will see later on, big larger trees may introduce problems. They become more like the model becomes so complicated, and we may run into problems like overfitting and issues with the interpretability of the tree itself. Okay, so then the feature that minimizes the uncertainty is the one we should select first as we are building the tree. And actually, there are that leads us to the next question, is actually, how do we measure the uncertainty? Okay, so there are very well-known metrics to measure the uncertainty. In this set of lectures, or in this course, we will focus on entropy. And with that, I think I come to the end of the first part. It's very introductory. Next class, we will dive deeper into how to measure the uncertainty using, or how to quantify the uncertainty using the entropy. I come to the end of this lecture. Thanks for watching, and see you next time. Assalamu alaikum.